Hi, my name is Soumya, and in this work done in collaboration with Professor Oliver Cromer, I will talk about dynamic inference on graphs using structured transition models. Our work takes inspiration from common human tasks such as picking up an object in one smooth motion, pushing a heavy door using the momentum of our bodies, or pushing off a wall to quickly turn a corner. All these tasks require complex dynamic interactions between the human and the environment. Enabling robots to perform such tasks is challenging and requires us to explicitly reason about the dynamic interactions and switching dynamics inherent in such tasks. A lot of prior work has focused on learning the dynamics of interactive systems using structural priors, that is, by adding a prior to dynamics model. For example, by modeling a system as a switching dynamical system, one can model the changing dynamics as explicit dynamic modes. This approach has an obvious limitation that the number of dynamic modes has to be pre-specified, which makes it hard to generalize to more objects. Graph neural networks, on the other hand, overcome this limitation and allow for the generalization benefits of popular graph-based approaches. Although promising, this approach suffers from scalability issues as the number of interactions increases and sample complexity suffers. We propose learning a time-varying sparse graph structure to help mitigate this issue. Furthermore, neither of these priors directly incorporate stability guarantees in the learned models or their ability to be used for long horizon predictions. We take inspiration from some prior work in this area to enable learning stable, locally linear models using graph neural networks. Finally, the problem of learning GNN-based models for optimal control is insufficiently explored. Learning stable, locally linear models enable the use of optimal control algorithms such as ILQR for long horizon planning and control of complex interactive tasks. Now I will give a brief overview of our approach and talk about it in more detail in the coming slides. First, given some sample trajectories, we learn the dynamics of interacting systems by simultaneously learning the dynamic graph structure and a stable locally linear model of the system. Next, we use ILQR and the learn model to plan for the predicted trajectory and contacts. During execution, we employ a combined reactive and predictive control scheme. That is, we use the learn model and policy to predict the robot trajectory and anticipated contacts, and also react to unanticipated contact events by updating the model predictions using contact measurement updates and replanning. Let's first talk about model learning. Our method has two main parts, the graph inference module and the forward dynamics module that are trained together. The graph inference module learns the dynamic graph structure. That is, it takes as input trajectories of fully connected graphs and outputs time-varying sparse graphs by adding and removing edges from the graphs as contact is made and broken. The forward dynamics module takes as input the learned graph structure and outputs stable locally linear dynamics for each node in the graph. The graph inference module first performs spatial aggregation on the fully connected graphs by passing them through an inference graph network. Next, information is aggregated temporally by passing the output edge embeddings through a GRU. The GRU outputs discrete probability distributions over edge types. This probability distribution is sampled to obtain edge activations, that is, active or inactive for each edge. Next, the forward dynamics module passes the learned graph structure through the forward dynamics graph network that outputs another set of embedded graphs. These node embeddings are then passed through a fully connected neural network that outputs parameters for a spring mass damper system for each node. This representation is chosen since the dynamics of a spring mass damper system are linear and can be constrained to be stable. Next, the learned stable locally linear dynamics are used to predict the next state. Finally, both these modules are trained together by minimizing the L2 loss between the next state predictions and the ground truth. The KLD loss term enforces that the learned graph structure is sparse. Having talked about how the model is learned, let's talk about the policy. We use ILQR as our policy. LQR can be represented as the solution to the following optimization problem, which outputs an optimal action and state trajectory. Starting with an initial trajectory, ILQR iteratively solves the LQR problem using the learned model to update the dynamics at each iteration until convergence. Next, we talk about the execution strategy and our robust control scheme. To make our controller robust to unanticipated contact events, we use MPC to combine our predictive controller with a reactive control scheme. In the predictive component, the learned model and policy are used to predict the robot trajectory and anticipated contacts using ILQR. During execution, the observed contacts are used to evaluate a posterior over the edge activations by using the predicted edge probabilities as the prior. Since GRU aggregates past information for future rollouts, this posterior can be used to update future predictions, which are then used for replanning. This makes the execution scheme more reactive to unanticipated contact events. We evaluate our method in simulation and in the real world by using the learned model for control using ILQR MPC. First, we consider the task of dynamically picking up an object and taking it to a goal location. The model is trained with a single object and used for control using ILQR MPC. We show that the model and policy generalize well as distractor objects are added to the scene. Next, for the task of dynamically picking up two objects and taking them to a goal location, we show generalization to picking up many more such objects than seen during training. For the task of dynamically opening a door, we show generalization in the presence of distractor doors. In the Isaac Gym environment, we learn the locally linear dynamics model for the Franca arm dynamically picking up an object and taking it to a goal location and use the learned model for control. Again, we show generalization in the presence of distractor objects. Finally, we conduct real-world experiments with the Franca arm performing a dynamic pickup task using a learned interaction model. Thank you.